I'm here with Dennis Baumann of ETH Zurich. He is a researcher for the soft robotic fish project, and he will explain you a little bit more about his project today. So Dennis, can you provide an overview of this project and its main objectives?
Yes, of course. So the project aim is to be able to collect environmental DNA in marine environments. So that means we go into the water with a special kind of filter that's able to capture environmental DNA particles. Right now, this is one of the state-of-the-art methods for biodiversity surveying. That means to control what kind of species live in a certain environment. At the moment, the gathering of this environmental DNA is mostly governed by people diving down with gas bottles and manually collecting the water in the DNA filter. So this actually creates a very disturbing environment for all the marine species living there. So our main goal was to create a platform that is minimally invasive and that would not disturb the animals or disturb the animals as little as possible, actually. So our idea was that we create a soft robotic fish. So the fish mimics the appearance of different other species that are given in this environment. And also by actually not having any propellers on it. So we actuate with a tail that does significantly reduce the amount of noise that is produced by the robot. And of course, the fish can navigate autonomously. So there's also no need for any human diver interventions or any cables attached to the fish. In addition, we also supply a compartment for an eDNA filter, and then it can automatically pump the water through there and capture the eDNA. The fish then can simply return to the surface. You can pick it up. You take out the filter and you send the filter to a bioanalysis lab.
So you say the fish moves autonomously. Could you explain a little bit more in detail how this autonomous navigation works?
Yes, of course. So the way we navigate underwater is we kind of copy what fish do. So in a rough sense, we use the Earth's magnetic field to generate a compass heading. So with this compass heading, we can generate a rough trajectory. And then to avoid obstacles locally, we use a camera supplied with the Kowa lens, of course. And we use the image captured by the camera to produce a map of obstacles and free water, basically. We do that by using an autoencoder network. So we take in the full RGB image, we run it through a neural network, and it produces a segmented map of obstacles and background water. And then through some trigonometric calculations, we can figure out a good path for the robot to take. So this means we navigate roughly, globally, with the Earth's magnetic field. And then locally, to avoid obstacles, we use a neural network to generate a segmented obstacle mask to then successfully avoid the obstacle.
And why did you choose the Kowa lens for this project? What is the characteristics that make it work very well for this project?
So in our project, we do not use any other sensors for perception of the environment, except a pressure sensor. So usually you would use a LiDAR, so a laser sensor that can scan the environment. Or what is also typically used in underwater navigation is a large sonar, but that is unfortunately not available in our size and price range. So a cheap and viable option is a camera. So we only use visual perception with the camera output. It is very important that this image is very clear and nice. So we need a very good lens that will actually not distort the image too much, but still provide a very big field of view. And also the resolution of the lens is very good. So this helps with the AI algorithm actually detecting the obstacles. So on the one hand, the Kowa lens provides very good resolution and a clear, not distorted image. And then on the other hand, we found that the ruggedness of the lens is also very high, which is in our case also very important because underwater, the environment is really harsh. Also, since we have to enclose all the electronics, this also includes the camera and the lens system. This means that the heat buildup in the head is also very high. And we found that the lens does not distort the image with increase of temperature in the head. And it's also very robust against external forces. So, for example, by dropping it or by applying a large amount of pressure, by installing the camera, installing the lens, we found that the lens is very capable of handling harsh environments.
What were your main challenges in the development, and how did you overcome them?
So the main challenge was that the whole robotic system had to be underwater. So that means we have to provide a waterproof housing, which is not trivial to say. It is quite difficult because you cannot just provide a rectangular encapsule because of the hydrodynamic drag that would create. So you need a very special kind of 3D surface to actually move forward somewhat efficiently. That means you have to create your own custom waterproof compartment. And this is something that is not trivial. So we had a lot of trouble actually producing this kind of compartment, which means that a lot of the testing time that we could have spent developing algorithms to navigate autonomously or to test how well they function were rather difficult to do because we did not have a waterproof enclosure until, rather quite late. It took us quite a long time to actually get everything waterproof. So I would say the most difficult part is really the testing environment. It is far more difficult to test any system underwater than it is to test it in air.
So at what status is the project now? Is it still in a trial status? And how were the first trial, or is it already commonly used in research?
So at the moment, the project is more in a trial status. We are now focusing on improving the system. So that means we want to improve the robustness of the mechanical system as well. So we want to improve the mechanical system to provide a more reliable source of propulsion and, of course, steering maneuvers. And then on the other hand, we are also working on producing more robust autonomous navigation algorithms. So this might also include additional sensors in combination with the camera and the Kowa lens. And introducing another sensor paired with the visual perception, this could give us very reliable autonomous navigation in waters that are also very turbid. So, for example, in our lakes in Switzerland, it is very difficult for us to actually navigate somewhat successfully because the turbidity is so high in the upper layers of the lake that we cannot actually see anything. So compared to the ocean is quite clear. Like we could say there's quite a improvement in visibility in the ocean. So we are able to navigate in the ocean, but we are currently unable to navigate in normal lakes. So our goal is to introduce a second sensor that can do perception in very turbid environment, and then pair it with the visual sensor to get the most possible best autonomous navigation results out of it.
So the goal is to make it usable in any underwater environment.
Yes, exactly. But we have to specify it cannot go too deep. So we have to stay around above 20 meters of depth. But the goal is to make it very reliable and versatile, so that researchers can actually use it to successfully and efficiently gather eDNA data. And this would introduce a very minimally invasive way of doing biodiversity monitoring, which is currently very much at the need because of climate change. It is very difficult for us to actually measure how the oceans are deteriorating or developing, we could say. So the need for having eDNA samples from the ocean is actually there.
How do you want to make this technology more known to the marine research community?
So I guess social media and different newspapers or news broadcasters are always a viable option. We have also had quite a good track of publicity in the last few weeks. We've had, I think, Tagesschau, the German Tagesschau, did a post that has around 2 million views. There's also Reuters made an article about us. So we're quite good on track to making us to like spreading the news. But in a more academic way, we also want to publish a research paper in the next half year, which would also give us a more, I guess, established presence in the academic community, and which also might be quite nice to partner with a biological lab that does these kind of eDNA extractions and analysis. So ideally, we would want to write a journal paper that will actually combine the soft robotics lab and a biology lab together. And that way we want to actually present our platform to the research community.
Do you think this technology has the potential to be used also in other areas of application besides research?
In my opinion, this is more of a research platform. There's another way you could utilize it is by doing this in large scale fishery, actually. So you could deploy a swarm of these robots to swim around the ocean, and then they could perhaps try and track big scale swarms of fish, and then actually send the information to the large fishery boats to pinpoint the swarm. And it's also a way to gather information about what species of fish is in the swarm. So ideally, I would wish that it's only used for research. So I wouldn't be super happy about them using it to increase the productivity of the fishing vessel. So in my mind, it is more of a research platform.
And what does it for you personally mean to be part of this project? So what is the angle of this? What interested you? Is it the marine research? Is it the autonomous navigation? Or what does it mean for you personally?
For me personally, I've always been very drawn to the ocean. So it has always been a desire of mine to also protect the environment, or at least to say the ocean environment. And on the other hand, while studying here at ETH in mechanical engineering, my interest is more drawn to robotics and autonomous navigation. So with this project, I was able to combine both my desire to protect the ocean and also my desire to learn and progress in the field of autonomous navigation.
And if you look beyond this robotic fish project, are there any other projects you are dreaming to work on or thinking to work about in the future?
So for the near future, I will still continue working on this robotic fish. In a more long-term sense, I'm not quite sure what kind of projects will come along that I will be a part of. But generally, the interest is more in robotics and autonomous navigation. In an ideal world, it would be able to combine this with a strong impact against climate change. So ideally, a project that would include robotics and sense of environmental preservation would be ideal for me. But I have not pinpointed any specific projects, to be honest.
Okay, thank you very much.